What is that? Load scheduling works by unrolling and then interleaving the body of the loop, right? What is that? The first one, out is like R0 is assigned to out, and R1 is assigned to in, and R2 is assigned to CA0, and R3 is assigned to T, and R12 is for CA1, and R14 is for character number 2. And this is for character number 0, this is for character number 1, and character number 2. Is it right? So once it is done, I'm I'm making use of the stack pointers here, right? What is that? I'm just making use of the stack pointer. That is each value. Once you read each value, it will be pushed on the top of the stack. So come to the loop here. In the first instruction, what you have, you are loading the first character into CS0. CS0 is nothing but register number 2, and in the next cycle we are loading second character A1, which is nothing but 12 R1. In the third cycle, what you're doing is that we are loading into C2. What is that? Register number 14. We are loading it. That is, character 0 is loaded into register number 2. Character 2 is loaded into register number 12, and character 3 is loaded into register number 14. So why you are doing is that there is an interleaving of the things, right? When the first load instruction has been executed, it is still not available for usage. So what I'm doing is that I am doing in one more load instruction, right? Still it is not available, so I am doing in one more load operation. By that time CA is available, right? CA0 is available. So what I'm doing is that I make use of that, and I'm converting into a lowercase letter. Look at this one. Subtract t comma CA0 hash of a. We are just subtracting the character with a, and whatever you have, is it less than z or not? If less than z, what I'm doing is that I am storing it into CA0. And similarly, you look at the second one instruction, right? By this time CA1 is available for processing, right? The character 1 will be converted into lowercase letter. The character 1 will be converted into lowercase letter. Then by that time character 2 is also available. So we are doing we are performing, or we are converting character 2 into lowercase letter. Is it right? Then what I am doing is that I am appending it to out. The character 1 will be appended to out. Character 2 is also, sorry, character 1 is appended to out, and character 2 is also appended to out. Once it is done, I'm just looping it back. Just looping it back. If there are any other elements in the list, what I'm doing is that I'm just again loading 3 instructions, 3 characters at a time, and I'm just forwarding here. I'm just forwarding here. So one more thing is that all these values will be pushed on the top of the stack. That's fine. What what they are doing is that the return address will be stored on the top of the stack. So these 3 instructions are important because they are going to hold 3 recent characters from the given input string. So but the problem is that, let us take for example, if I have only 2 characters, let us take my string is only of 2 characters in length, but I am trying to load 3 characters into the register. That is, first character will be loaded into CA0, and the second character will be loaded into CA1, but I'm trying to load a third character which is not existing, or which is out of the array boundaries. It is out of the array boundary. Still, I'm trying to load that character into CA2, which is illegal. Is it right? And even in some cases, if I'm reading 3 characters at a time and loading it into CA0, CA1, and CA2, but by the time I'm just finished, like it will not check whether you have reached the boundary of the string or not. right? That is one major drawback of the unruling. But apart from that, major advantage here is that you're just interleaving the interleaving load instructions or overlapping the load instructions, so that it is going to improve the performance at all the cost, right? This is one. RDRB, we are loading the first character, second character, and the third character. Anyhow, once you call the load instruction, it's not available for the immediately available for the processing, so we have to wait it. While waiting it, what I'm doing is that I'm loading one more character into CA1, so still it is not available. So what I'll do is that instead of waiting, I load one more character into CA2, right? Once it is done, I'll actually take out the CA0. CA2 is still not available, so what I'll do is that I'll take CA0, that is a zeroth character, and I'll process it and convert it into lowercase letter. Then CA1 is available, what I'll do is that I'll take it out and I'll convert into lowercase letter. And similarly, CA2 is anyhow available. It is being converted into lowercase letter. Then what I'll do is that I'll append it to the out. I'll append it to out. Then is if there are any other characters remaining, I'll just loop it back. I'll just loop it back. Right. Once everything is over, what I'll do is that I'll return the execution control back to the point where it has been called. That is retrieved from the top of the stack. We have pushed it on the top of the stack, right? LR has been pushed on the top of the stack. So at the end of the list, at the end of the subroutine call, what I'll do is that I'll retrieve from the top of the stack. That is a return address. I'll take it out from the top of the stack and load it to the PC. So it becomes a current executable instruction, and then I'll continue to execute the remaining instructions. Okay. So these are the two methods which I have worked with. So we have worked with. So this is a simple C program to convert your uppercase letters to lowercase letters. All right. This is what the unoptimized instructions what you have it. That is, it is not yet been optimized. It consumes uh, more number of system clock cycles, right? So how many clock cycles it requires? Just count it here. How many instructions or how many cycles it requires?
Three
Yes,
cycles, sir.
this one,
Three,
this one, LDRB.
three,
I'm talking about the entire subroutine. How many cycles it requires? This is two cycles. This is one. This is one. This is one. This is also one. This is one. This is three, and this is one. How much it is? 2, 3, 4, 5, 6, 7 plus 3, 10 plus 1,
11, sir.
11,
11.
11 cycles it
11.
actually required.
11.
11. This is two, right? Two cycles to finish it off the execution, right? And this is one cycle, total 3. This is one more cycle, 4. This is 5, 6, 7. Here is the branch instruction, right? Branch instruction. So 3 more instructions, 3 more cycles. It comes to 10, and this requires only one cycles. Totally is 11 cycles it requires it. 11 cycles it requires it. Come back to this problem. How many cycles it requires? Can you count it? For each loop I am talking about, you leave this one. It requires how much?
10.
Plus 3.
10.
3 plus 2, 5, 5, 6, 9,
7, 8.
10, 10 cycles
10.
it requires for each loop.
Has.
You forgot about this because it is done only one time. It has been done for only one time, so it requires 10 cycles to execute the loop. That is 1 plus 1, 2, 3, 4, 5, 6 plus 3, 9 plus 1, 10 cycles it requires. So we have optimized it such a way that we have reduced it from 11 cycles to
10 seconds.
it requires 10 cycles. There is an saving of one cycle, right? But it looks amazing, right? For one cycle, uh, why you're fighting for so much, right? So this is for only one character. Let us think for I want to convert some 10,000 characters from uppercase to lowercase letters. Actually, how many number of cycles we are saving it? It is 10,000 cycles, right? Where 10,000 cycles we are saving it. That will add much to the performance of the system. So that is what the whole idea of preloading. Come back to the unrolling, right? How many cycles it requires? We just look at how many cycles it requires. This is two, two, two. That's six, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 plus 3, 21 plus
24,
3, 24.
25,
That is for
25,
24 instructions,
25,
24 cycles for 3
25.
characters. 24 cycles for 3 characters, because we have converted simultaneously 3 characters. One character, CA1, sorry, CA0, CA1 and CA2. So we have converted 3 characters simultaneously, right? So even if you consider this one, it comes around 26 characters, 26, right? So we have converted in each loop. We have converted 3 characters. That comes around 26 characters. Sorry, 26 characters. There is a there is a saving of 4 cycles, right? There is a saving of 4 cycles. And even if we leave this one, if we leave this one, so if you consider only the loop up to branch instruction, it comes around 24 for 3 characters. For 3 characters, we have saved 6 cycles, right? Approximately, we have saved 6 characters, sorry, 6 cycles. Like this for 10,000 characters. For 10,000 characters, it comes around how much, right? Or let's say for 1,000 characters, it is three. How much it is for 1,000 characters? 333 multiplied by 3. Sorry, 6. It comes around 300. Sorry, 2,000 cycles, right? We are saving somewhere around 2,000 cycles for only 1,000 characters, right? For 10,000 characters, we are saving somewhere around 20,000 cycles, which is very big one, right? Here we have saved 10,000 cycles, whereas here we have saved some 20,000 cycles, right? But there are obvious disadvantages with respect to unrolling. What is that? The routine is more than double the code size of the original implementation. You look at this is my original implementation, right? This is my original implementation. Number of instructions are very few, right? Hardly 7 to 8 instruction I have it. But if you look at the unrolling, the number of instructions are very huge. The code sizes or the code density is very high, right? Look at this one, around 20-25 instruction I have written. Instead of only 8 instruction, I have written I have written how much? 20-25 instruction. That is the biggest disadvantage of the unrolling. The routine is more than double the code size of the original implementation. It is more than double the size of the original implementation. And the performance can be slow for very short strings. If the number of characters are very small, let us take, I want to convert a string of only 10 characters. I want to convert a string of 10 characters, then this unrolling is of no much, it doesn't make much difference, because the number of the code size is very large and it becomes much slower. But it is very efficient when the number of characters in a given strings are very large, let us take it is about 10,000 or 20,000, then you can find some optimizations. That is, the performance can be slower for very short strings, right? If the strings is very small, then it's not going to give you a good outcome. Stacking LR causes additional function called overhead. In this case, what we are doing is that we are using we are putting LR on the top of the stack, right? Right? It's an overhead actually. It's an overhead, right? Causes additional function called overhead. The routine may process up to two characters pointlessly before discovering that the lie beyond the end of the string. Look at this one. I have already told you, if the number of characters is if it is a multiple of 3, if it is multiple of 3, then there is no big issue. Let us say I just wanted to manage, or I just wanted to uh, convert, let us take only 7 characters. I want to convert only 7 characters. In the first iteration, in the first loop, 3 characters will be get converted successfully. In the second character, sorry, in the second loop, 3 more characters will be get converted. In the first third iteration, CA1 will hold the seventh character. CA1 will hold the seventh character, whereas sorry CA0 will hold the seventh character, whereas the CA1 is holding a character which lies outside the character string, or which lies outside the boundary of the string character. And in fact, CA2 is also pointing to pointing out of the boundary of string. So that's why these two are pointlessly pointing outside the characters, or outside the string. So that is what the major different disadvantage of the unrolling. So first one, it is the routine is more double the code size of the original implementation. It is more than, it is the code size is huge compared to the original implementation, and the performance can be slower for very short string. If the string is very small, let us take it in terms of it's only in terms of the double digits, then it's the performance is going to slow, right? It is slower compared to the larger strings. And stacking LR causes additional function called overhead. You are creating an overhead by just pushing LR on the top of the stack, and the routine will process up to 2 characters pointlessly. That is very important. So even though there are no more characters in the string, still you are pointing to characters which doesn't lie within the boundary of the string. And the next one, how to assign, or how to assign the registers. There are 16 registers, right? There are 16 registers beginning from 0 to 15, right? You can use 14 of these 16 of the ARM registers to hold general purpose data, right? The remaining 2 registers, that is R15 and R14 and R15, meant for some special purpose, right? R15 is meant for the stack pointer, and R14 meant for the stack pointer. It's considered as a stack pointer, and R15 is considered as the PC, that is a program counter addressing. Program counter registers. And the remaining 14 registers are of general usage, right? The other 2 registers are the stack pointer, that is R13, and the program counter is R15. I have told that it is R14, right? So R13 is considered as the stack pointer, and the program counter register is R15. It is, right. So the remaining 14 register is of general purpose usage, right? So look at the one example of finding the things here. We are saving, or we are pushing uh, all the 9 registers on the top of the stack, right? With the LR as well, And what I'm doing is that I'm storing uh, the contents of SP into what? 9 register beginning from the register number R4 to R12, and the return
R20.
address LR will be stored into PC register. LR will be stored into PC register. In this way, we can make use of the registers very effectively. And how to assign variables to the register numbers, allocating variables to register number. The best to start by using names for the variables rather than explicit register numbers. Instead of using the explicit register number, what I can do is that we can assign a variable. This allows you to change the allocation of variables to register number easily, right? You can change the variable name so that you can easily change the register number as well. What do you mean by thing is that variable in the sense that look at this one. This is one variable. Register R0 is meant for out. Instead of reading R0, what I can understand is this R0 is holding an output string and R1 is holding an what we call it as input string, and R2 is holding CS0, and R3 is having holding RT, and so on, right? These are the variables. If I want to change the register, let us say I want to store output register in some other register. Let us say I want to store it into R5. So what you do is that you simply change it to R5. That's all. So everything will remain same. It is. You need not have to change anything here, right? If I want to store in some other register, let us take R7, you need not have to change anything here. Instead, what you do is that you just change it as R7. That's all. So everything will remain as it is. That is what the meaning here, right? So it is best to start by using names for the variables rather than explicit register numbers. This allows you to change the allocation of variables to register numbers easily, right? You can uh, change the registers by just using a different variable name. You can even use different register names for the same physical register number when their use doesn't overlap, right? You can use the different register name for the physical register number when there doesn't overlap. You can use different register names for physical for the same physical register number as well. And the specific register numbers do not have do not have specific rules at all, right? They don't have register specific rules at all. So cases where the physical number of the register important when you want to make use of the physical number of the register is important. So first case is that argument registers, right? It is the ATPCS convention defines that the first four arguments to a function are placed in the register R0 to R3. First four arguments will be stored in R0 to R3, and the further arguments are stored on the top of the stack. The return value must be placed in R0. That is very important. So you are writing the functions, right? You're writing the functions with n number of arguments, right? And if you let us take, I have four arguments in it, or so let us take, I have written five arguments in it. Then the first four arguments will be the register R0 to R3. That is R0 will hold the first argument, R1 will hold the second argument, R2 will hold the third argument, R3 will hold the argument. And what about the remaining argument? Top of the stack. It goes on the top of the stack. That is further arguments. That is argument number 5, argument number 6 would go on the top of the stack. The return value must be placed in the register R0, right? The return value from the function will be stored into the register R0, right? The register is used in a load or store multiple. Load and store multiple instructions. LDM and STM operate on a list of registers in order of assigning register numbers. Right? It is you are storing the values in their assigning register number. If R1 and R2 appear in the register list, then the processor will always load or store R0 using a lower address than R1, and so on. Right? R1 will be loaded with the lower address value, and R0 will be loaded with the lower register address value, and R1 will be loaded with the higher register value address, and so on, right? So that is for that reason you are using it in the load and store multiple load, and load storable double word. This is for the 32-bit number.